Are you guys excited about it? And hopefully finish most of data dependence handling today and start control dependence handling. And then in the next lecture, we'll finish how to handle branches in fancier ways or in higher performance and more efficient ways. So hopefully it should be exciting. That has been a topic that people have worked on for decades. How do you figure out what is the next instruction to fetch in a pipeline processor? And we'll see the importance of the problem as well as many different solutions to handle it. But today we'll focus on data dependence handling to begin with. But I guess our usual reminders, don't forget your homework. You'll need to fill in the microcode. And in microcode, I think every single column is a single bit, right? In that Excel file where you need to fill out the microcode. I think I had a question related to that earlier today. So don't put multiple bit values in a single column. Okay. And homework 1 solutions were out, so hopefully if you attended the recitation session Friday, you should know this. I didn't announce this, but. Lab assignment 2, it's due February 15th. Get started. Some of you are already considering the extra credit, which is good. And when you do the extra, before doing the extra credit, you should complete the first part, the normal credit part. But when you do the extra credit, that's dependent on your creativity. So the design decisions you make, as long as the design is functional, we'll evaluate your design based on the functionality and your justification of your design decisions. Of course, if you optimize for performance, that's good for you, right? You'll learn something even more, but you have limited time. We understand that. Okay. These are homework 1 grades. Looks like most of you are doing pretty well. Homeworks are for your benefit, so this won't necessarily significantly affect your grade. But you can see how you're doing by referencing this chart. And are they available now, the homeworks? Are we going to hand them out today? Oh, we're still waiting on one? Okay. What happened to that one? That's an example of data dependency. You're dependent on one homework. You're stalling. Okay. So they will be distributed. You'll get these. But you already know the solutions. And this is a Lab 1 score distribution. I'm happy to see that the curve is actually like this. It's like an exponentially increasing curve going toward the right. That's a good thing. If you're doing well on the labs, that's good. If you're around here, I'd encourage you to get your lab correct, just for learning. We won't give you extra credit for getting it correct, but it's good for you to learn. So the average is 81%. Again, these are mainly for your benefit to see where you are in the class. And if everyone does 100, everyone gets A's. Nice, right? Or 90s. I'm not going to curve just based on this. If everyone does really well, everyone gets A's in the class. Okay. Some readings for the next few lectures. You can continue reading Patterson and Hennessy chapter. I had assigned 4.5 to 4.8. 4.9 through 4.11 is more advanced. And I'll assign this paper, which could be a little bit tough to crack in the beginning, but you'll learn a lot. This is a relatively old paper now. It's about the microarchitecture of superscalar processors. It walks you through a superscalar, which is wide fetch processor as designed today. Well, today meaning 1995. But a lot of the principles already still apply today. So you'll see a lot of the concepts that we will cover in the lecture. Not only pipelining, but also advanced pipelining, data forwarding, interrupt and exception handling, and out-of-order and superscalar execution concepts are covered in this relatively long paper. And it's a good reference. I don't think there's any book that covers this that concisely. That's why I'm assigning this paper. Okay, make sure you read it. You'll enjoy it, I think. And a lot of things will become, the lecture will become much more interesting, I think, if you read this. Okay, today we're going to do a deep dive into pipelining and especially talk about dependence handling. The basic idea you remember, I'm going to go through this relatively quickly again. We're going to do pipelining. We divide the instruction processing cycle into distinct stages of processing and process each instruction at a different stage, right? The benefit, it increases instruction processing throughput, or IPC, instructions per cycle. Downsides, we've discussed several downsides, and we're going to discuss more downsides today. And we're going to fix some of those downsides, hopefully, with new techniques. Because fundamentally, it's a good idea, because we would like to increase processing throughput. But downsides we would like to handle somehow such that we make this a really good trade-off. OK, this is the execution of 4 independent ads, right? This is why you would like to do pipelining, because you can improve throughput. But is life always this beautiful? No, right? But you handle with the non-beautiful, you deal with the non-beautiful parts. This is not so beautiful because these are all independent ads, right? You don't always get these 4 independent ads. And this is, again, to refresh your memory, this is the pipeline we've looked at, we've designed, and you're going to design. You have a load instruction followed by an independent subtract instruction, and these can execute in a pipeline fashion. When one instruction moves to the next instruction moves to the stage the previous instruction was in. So you can complete these instructions. Again, life is not that beautiful. We'll see what happens if this subtract instruction is dependent on the load instruction. You will not be able to move the subtract instruction nicely in the pipeline. Right? So what can we do about it? So this is basically instruction pipeline is not an ideal pipeline. We don't have identical instructions going through the pipeline. And not all different instructions do not need all stages. Difficult to balance the different pipeline stages. We've talked about this. We're not going to talk about it in this lecture. And operations are not independent, which will be the subject of this lecture. Instructions are not independent of each other. Instructions are different, and they're not independent, which means that pipeline is not always moving. Pipeline stalls. And we're going to try to minimize those stalls. And these non-idealities lead to fundamental issues in pipeline design. Always, this is again very fundamental, right? The problems cause the issues that you need to solve. These are the problems, and people have worked on these problems to solve them. They try to balance the work in pipeline stages, how many stages and what is done in each stage. That's not something we're going to cover significantly, but if you're interested, I'm happy to give you references related to that. This is more of a design issue. How do you balance the critical path across different stages, right? We'd like to keep the pipeline correct, moving, and full. And all of these are important. Correct, you would like to, in the presence of events that disrupt the pipeline flow, how do you maintain correctness? And how do you keep the pipeline full? And these are the events that disrupt pipeline flow. Dependencies in terms of data and control. Resource contention, which we've covered. I'm not going to cover, but hopefully you remember. And handling long latency operations. And the third is handling exceptions and interrupts. So we'd like to improve pipeline throughput by keeping the pipeline moving, full, and correct. Okay? So let's go into data dependencies again. This is again a review. Remember, there are 3 types of data dependencies. Flow dependence is the true data dependence. You have a read from a register that was written by a previous instruction. Output dependence is a fake dependence, if you will. 2 instructions write to the same register. And you have to maintain the semantics of those writes, the order of those writes. And I'll get to this in a little bit. Because one of you asked, why does this happen? And there are actually reasons why this happens in the dynamic instruction stream. Which ones cause stalls in a pipeline machine? Basically, for all of them, we need to ensure semantics of the program is correct. OK, and we've talked about this, so I'm not going to cover this now. This is, again, a review. So these are data dependence types. This is read after write. This is the only true dependence. This instruction really needs this value that's produced by the producer instruction. You can think of this as the producer and the consumer. Anti-dependence, here, this instruction is writing to register 1 that is read by a previous instruction. Well, here, fundamentally, the register 1 is really pointing to 2 different values, right? There's a value in register 1. It just happens to be stored in register 1. There's another value produced by this instruction which has no relationship with this value that was previously stored in register 1, right? Here, it's really a name dependence, right? It's not really a data flow dependence. And that's the fundamental distinction between these dependencies. You're storing a totally different value in a storage location that happens to be the same, right? In a sense, that's why I call this a fake dependence, right? If you had infinite number of registers, there was no reason for the compiler to store the second value in R1, right? Because those two R1s, the values in R1 between those two different instructions have no relationship. Basically, these dependencies are due to limited number of architectural registers. You can eliminate them if you had an infinite number of architectural registers. These two dependencies, the anti and output dependencies. And the last one is the output dependence. So you can imagine why this happens, right? This happens because the compiler doesn't have enough registers and it needs to allocate the value produced by this operation into a register. So it happens to pick R1 because R1 is not needed. The previous value stored in R1 is not needed later on. So it's easy to see why this happens. It's a little bit harder to see why this could happen, although this is not. So let's ignore this R3. Here R3 is used because there's another dependence coming in, as someone said in the last lecture. So output dependence, these two instructions are output dependent on each other because they're writing to the same register. Again, the reason is the same. The compiler didn't have enough registers to store the value of this instruction in a different register. If it had enough registers, this could have been R1000. So why does this happen? So output dependencies actually can happen in a pipeline even without this R3, the previous version of R3 being used in the pipeline. So let me give you an example. Can anybody guess, actually, before I give you the example? Why could you have two instructions in the pipeline? This is without that example. Let me give you the example. You have R3 written by, let's say, an add. And then you have some other instructions. None of them use R3. And then some other instruction that writes to R3, let's say a multiply. And these happen, let's say, one instruction here. Actually, let me change this a little bit. Maybe I'll do it load to motivate the example. These two instructions are in the pipeline at the same time, even though this previous version of R3 is not going to be used. Yes?
In an out-of-order machine, it can keep walking down the pipeline, execute multiply, and then have the load come in on top of the result of the multiply.
That's right. An out-of-order machine, you can go and look ahead and find this happens a lot. That's right. Let's say this is not out of order. We'll cover out-of-order execution. Yes?
If the load takes a while, you need to make sure that you wait for the load to finish before you write the multiply result.
That's right. But why would there be no instruction that sources this R3 in between? Yes? Okay, that's good. So the compiler did something right here. Let's take a look at why this could happen. Let's say you have this control flow. This is, do you guys know about the control flow graph? Basically, control flow graph is a graph of the control flow of the program. You can think about a program as a graph of what consists of basic blocks. And a basic block is a unit of instructions where a number of instructions, a block that has a single entry and single exit point. So here, a basic block, let's say you have add, multiply, add, branch. This branch now breaks the block. Now you have two blocks where this branch can go to. This could be the next target address of the branch, and this could be the fall-through path. Right. So a basic block is a block of instructions with a single entry point and a single exit point. Make sense? Yes. Single entry, single exit. Should use a better one. Okay. One more. Okay. So here, now you have two paths after the branch, right? let's say we have multiply. Let's say you have a load instruction here. And let's say, okay, let me mark this load. Let's say this is our load that we're looking at. And let's say this is our multiply that we're looking at. That's the first instruction in this basic block. So compiler can actually reorder instructions in the instruction stream. What the compiler might do is, this load is writing to R3, right? And this multiply is also writing to R3. Because the compiler may predict that this load will take a long time, because loads are not always one cycle, right? They could be 10 cycles. The compiler can move this instruction before the branch. Now the load is writing to R3 here, right? Such that the load executes early on, right? It does prefetching, for example. And if you look at this code works correctly regardless of which way you go in the branch, right? Because you're loading R3 here, assuming no one writes R3 here in between. Let's assume that. You're loading R3 here, and R3 is the value that you would have needed anyway when this load was here. You're loading R3 here. If the branch takes this path, it's OK, right? Because this multiply is going to overwrite R3, and you're going to have the right value of R3 afterwards. So why could the compiler do this? Let's say this is a frequently executed path in your program. So the compiler somehow determines that this branch, 99.9% of the time, takes this target. And the compiler now can schedule instructions such that this path is optimized. Make sense? And how does the compiler determine that this 99.9% of the time you execute this path? Any guesses? It's called profiling, right? The compiler can actually profile the code. And this means that the compiler can run an input set, representative input set, run the program before the actual run, and figure out how often each of these control flow paths are exercised, how often each of these arcs are exercised, how often is this branch taken versus not taken. And based on that information, the compiler can decide scheduling of these instructions. And once the compiler finds that this is the most commonly executed path, it can schedule the instructions, reorder the instructions such that you get a faster execution schedule. Right? Make sense? So there is a reason, there may be a reason why the compiler moves this load earlier. Now, if the load is moved earlier, but during runtime, so profiling is done at compile time, but during runtime, when the program really runs with a different input set, this branch may be not taken. The branch may fall through, right? Which means that you've executed this load. So what you have in the pipeline is load that loads into R3, this branch, and assuming we've handled the branch nicely. And the next instruction in the pipeline is multiply R3. Now you have a write after write dependence in the pipeline without reading the value that's produced in between, right? So the scheduling of instructions by the compiler can lead to all of these different dependencies. Yes?
Is there any kind of compiler in the current industry that actually uses this?
Oh, excellent question. Almost all compilers actually use this kind of profiling today. GCC, for example. You could enable GCC to do this kind of profiling of code.
How do they generate this sample inputs?
So that you need to give it to GCC. You can actually look at it. The programmer provides the compiler with a sample input set. And that input set is important, right? And the compiler takes that input set, runs the program, figures out which paths are executed, and then does the scheduling. Now, we may cover superblock scheduling. Actually, compiler can merge these blocks too. But we'll not get to that right now. But just for your benefit, it's called a superblock scheduling. You don't have small blocks, but you can merge these blocks such that you can do better optimization. Now you have more instructions you can reorder from. But you have a good point, basically. How do you choose the input set to decide this, to decide to make this optimization, right? That's important, because with one input set, this branch may be taken 99% of the time. With another input set, input to the program, this branch may be not taken 99% of the time. Right? So if your input set is not representative of your runtime input set, if your compile time profile input set is not representative, I guess I'll say not representative of your runtime input set, your compiler can make scheduling decisions that are not desirable. Right? It can optimize for this path, but actually you're executing this path in the program in real execution, real run. And that representativeness is important. This is a fundamental problem with profiling. When you profile the code at static time or compile time, you'd better have a representative input set that will be representative of what you will actually execute at runtime. And this is a difficult problem, as you might imagine, right? Because programs have many inputs. For example, when you're, running Excel, sometimes you're calculating your balances, sometimes you're doing something else, right? These are different input sets. Yes?
So, executing the load before branch, it only helps because you can loop around until memory is ready, and you can be ready faster after branch, right?
Mm-hmm.
But you're still going to execute one extra instruction if you fall through.
That's right. If you fall through, you're going to execute one instruction. But if this is 99.9%, you're probably not going to fall through. That's where profiling input set is important. Whereas if at runtime it becomes 50%, yes, that's the trade-off. You're executing one instruction unnecessarily.
But this only helps when you have an instruction like memory instruction where you have to wait at some point in time.
It could help with any instruction that is long latency. Right? Now we haven't gotten into long latency operations, but it could help. It's certainly it's usually employed with instructions that have variable latency. Sometimes you need to wait longer, sometimes you need to wait shorter. With loads, it's variable latency, right? With caching, as we will see. If the load hits in the cache, it's quick. If the load misses in the cache, it takes longer. But you're right, it's mainly used for memory instructions. But it could be used for instructions that have variable latency or long latency. So this optimization, by the way, is called load hoisting. You basically hoist the load up such that hopefully by the time you need the value produced by the load, this R3, some instruction needs this R3, the load is done. Okay? Okay, so this is one reason why you can have a write after write dependency in the pipeline without any intervening reads to that particular register. There are actually other reasons. We'll cover branch delay slots in a little bit detail. You could imagine that branch delay slot being filled with an instruction that sometimes, with an instruction that causes a write after write dependency. But maybe when we get to that, you can remind me, or you can think about that. So there are many reasons, and the main reasons are actually compiler optimizations like this to do scheduling. Okay, any questions? All right, So pipeline operation example, this was our pipeline with load and the subtract independent of the load. These flow nicely. But what happens if the subtract were dependent on the load? Now let's rewind a little bit and imagine that the subtract is dependent on the load. If the subtract needs the value of the load is producing the value of register 10, this subtract, when the load in this stage, register 10 is not produced yet. Oh, wait. Well, okay, you got to imagine here. I didn't change the slides. Imagine that the subtract is actually sourcing register 10. How long can you fake yourself? I guess that's a test. Register 10 is not produced, which means that this subtract cannot move to execution, right? Register 10 is still not produced here. The load is accessing memory, so subtract needs to somehow wait here. Register 10 is available here, right? The load actually read the data from memory, and it's going to write to the register file. Only at this point, the subtract can get that value. Well, we're going to fix that problem. Make sense? So basically, somehow, if the two instructions are dependent, the subtract cannot move. And you've got to stall subtract at the right place. OK. I guess before that, stall is one option, but we'll see other options too. These anti and output dependencies are actually easier to handle in a pipeline machine, at least in the pipeline machine we designed here. This is a simple pipeline. There's no multi-cycle operations. What happens is, as long as you write to the destination register in one stage and in program order, you can handle them. But we'll see how to detect them also. You will need some mechanism to actually detect them for correct operation, and we will see why. Flow dependencies are more interesting. When you actually have a true dependence, that's a lot more interesting. And there are actually 5 fundamental ways of handling flow dependencies, all of which I intend to cover. The first one is easy, right? You detect the dependence and wait until the value is available in the register file. Simple. What else? Anybody read last year's slides or has ideas? Yes? Multi-threading. Oh, you're going fast. I thought no one would come up with that answer, but we'll get to that. You detect and wait. This is the worst possible you can do, right? What can you do if you detect? Well, here, one thing you could do is you detect that this subtract is dependent and wait until the value is written to the register file. But maybe something else you can do is you don't wait until the value is written into the register file, but you bypass the value. You forward the value when it's actually available. Because the value is available before it's written into the register file. Value is actually available right here, right? So when this load finishes its memory access, you could have a data path bus that takes that value and forwards it to the beginning or the end of the stage, such that the subtract that's waiting here can capture that value and move on to the next stage, right after the value is produced. You don't need to wait until the value is written into the register file. This idea is called data forwarding, and we will cover that in a little bit more detail. Of course, you need to detect when you can forward the data. Right? Yes?
Wait, is the detection happening on the hardware level, or is the compiler telling the hardware that there's this dependency?
So that's a good question. Well, the compiler is already telling the hardware there's a dependency based on the names, right? But this detection I'm talking about is happening at the hardware level. The hardware actually looks at the register names and checks if two instructions are dependent. And we'll see ways of actually designing that detection logic. Yes?
Go back to the slide for the so in this case, even if you bypass the value, you still waste cycle.
That's right, exactly. You may not always keep the pipeline fully full, but you would eliminate at least one cycle of bubble. That's a good point. And we'll see how that affects things. Okay, that's the other solution. Detect and forward the data to the dependent instruction. Not wait until the register file actually has the data. What else? Well, this goes to something you said earlier. You can detect and eliminate the dependence at the software level. So the software actually detects this dependence. In this case, there's no need for the hardware to detect the dependence. What does this mean? Well, this means that if you have two dependent instructions, let's say we have this load that's loading into R10, and we have this subtract that's actually reading from R10, the software knows what the pipeline looks like, and instead of putting this subtract right after the load, it schedules the instructions such that there is enough distance between the subtract and the load. So it puts, let's say, a no-op here, another no-op. I guess you will need a third no-op also. And then the subtract that reads the R10. Because the software knows what the pipeline looks like, the compiler knows what the pipeline looks like. And when the subtract can get the value from the load, it puts additional instructions in between, such that you don't need to detect this at the hardware level. Right? So this is, you can think about this as software-based detection, dependence detection. Or we'll call it interlocking, if you remember. I briefly talked about that. Basically, it's the software's job to ensure that the pipeline operates correctly. Right? And this may not need to be no-ops, right? Remember the example I gave over there? Maybe you can find some independent instructions to put over here. That way, this dependence is kind of eliminated. Hardware doesn't need to do the detection job, right? Make sense? And this is exactly the reason why those sophisticated techniques to schedule instructions were developed. To ensure that in the presence of these dependencies, you can keep the pipeline full without adding no-ops. So if you can find some instructions here, down here, that are independent of the load and the subtract, and you don't change the program semantics by moving them here, you can fill these slots, I will call them, with useful instructions, while still ensuring that the pipeline is full and the hardware doesn't have any dependency check logic. Make sense? Okay, that's the third solution. There are a couple more. Two more, actually. And if you find more, let me know. What else? I'll get to multithreading. So multithreading is one of them. What else can you do? You fetch this instruction, and this is a hardware solution. I'll give you a hint. You fetch this load instruction. Let's keep R10. It's writing into R10. And the next instruction is subtract. This is what the software is scheduled. Software doesn't do that. It's not that intelligent. And we don't want to employ the first two solutions. Can you do better? What else can the hardware do to be able to execute the subtract without waiting for the load? Well, yes. Good. Excellent. You can guess, right? You can predict. Predict is another fancy word for guess, actually. You can predict what the value in R10 would be. You don't know for sure because it's going to be produced, but you can guess and then keep executing. This way you can keep the pipeline full, right? That's the idea. This is called value prediction. Even though there is a dependence, the hardware predicts the value of R10. And when the R10 value actually becomes available, when the subtract, before the subtract is done out of the machine, you check whether the predicted value is the same as the produced value. So there needs to be some logic to do this verification. Yes?
This is a sophisticated guess, right? It's not like...
Yeah, it's absolutely as sophisticated as you would like it to be. You can make it much more sophisticated. You're absolutely right. You would like to make it much more sophisticated, right? And we're not going to go into that in detail, but if you're interested, we can talk. So for example, the hardware figures out that the value produced by this load is usually 0. Somehow, imagine. What you can do is have a table. When you fetch this load, you say the value in the destination register of the load will be 0. This can be called the value prediction table. Separate table. And when you fetch the subtract, you check this table for R10. And this could be maybe the value of R10, predicted value of R10 currently. Right? You use the source register to check this table. When the load executes, it updates this value that's produced in its previous execution. And most of the time it's 0. Somehow you have a mechanism that says, oh, most of the time in the previous executions, the value was 0. And I'm not giving you the exact hardware implementation of this. When this subtract is fetched or decoded, you index into this table with the source register, and you found out that that source register is most of the time was previously 0. And that's your prediction now. Right? You take 0 and execute with it. Execute speculatively. What does speculatively mean? Without knowing that that's the correct execution, right? You do something speculatively without knowing. It's speculative. And when the subtract when the value actually becomes available, you need to check whether that R10 is actually 0 at that point in time. And if it is, then you've eliminated the dependence. If it is not, well, now you complicated things, right? What do you need to do if it's not? Then you need to flush the pipeline, get rid of everything you've done, and re-execute from the subtract, right? Remember, and you can imagine how to implement this. We're not going to go into detail, but now this load is executed, subtract figures out that R10, it's sourcing R10, is 0, or predicted to be 0. Subtract keeps executing. And when this load actually finishes, writes into R10, at this point, subtract checks whether R10 was actually 0 before it writes back its result. If it is 0, everything is great. If it's not 0, now you need to refetch the subtract, right? You need to do something. Perhaps you've fetched other instructions here. You need to flush the pipeline. Get rid of every instruction in the pipeline that you've partially executed and restart the pipeline from the instruction that was mispredicted. Its value was mispredicted, right? It wasn't correctly predicted. Yes?
So other than this table, you will have another set of hardware that actually memorizes, okay, I did this prediction before, so that I will have to go back there.
That's right, yes. You need some additional state that's carried with the subtract that says, I've actually used the predicted value for the subtract for register 10, and the predicted value was actually 0. And you also need some additional hardware that somehow accesses the register file to get the real value that was produced by load, and then additional hardware to compare those two values. So it's additional complexity. It's not easy. Yes?
Can you, in the meantime, have executed, 1 or 2 more instructions, and those could have changed the register file? How do you undo that?
So the key is not changing the register file. The register file is changed only at the write back stage for this pipeline, right? As long as you make sure you don't change the architectural register file, this is fine.
So that would get complicated with any forwarding that if you can use more than one, I'm assuming, to handle flow dependencies.
That's right, but as long as you write to the register file at the very end, there's no problem. You can forward incorrect values here, as long as you detect that you've done something wrong for the first predicted instruction before any harm is done, meaning before any speculative value is stored into the register file, you're fine. And we will see ways of doing that. But in this pipeline, it works nicely, right? Because register file is written over here only. And if you detect a misprediction, you just flush the pipeline, get rid of all the instructions. And we will see how to do that, actually. Okay, yes?
Does that mean the register file always sits in the first few stages of the pipeline? Because that will make sure you have whatever you bypass or whatever else you do goes to the later stages
That doesn't what?
Because like if your register file sits in the first few stages of the pipeline, you will have a lot of flexibility in later stages because you can bypass and those kind of stuff. But as long as your write back is to the first few stages, right? So now you're I guess I'm just complicated.
Okay. Okay, maybe you can think about it and we can talk about it afterwards. It's not about where the register file sits, but when you actually write to the register file, right? If you want to maintain correctness, you would like to write to the register file known correct values at the very end. Okay. This will become more clear when we get to actually control flow handling, because we'll need to do something similar, right? When we fetch the next instruction, what is the next instruction after a branch? So we'll need to, again, guess the next instruction. At least that's going to be one of the methods. One of the methods in branch handling, I'll give you, I think, 6 methods for handling branch control flow dependence, and one of them will be guess the next instruction. Okay, I guess what's the 5th way? You said multi-threading. Well, 5th way is actually nice and beautiful. You don't need to worry about any of this. You say, why should I worry about this, right? Do something else. What does that mean? Well, that means, I guess I don't have it here, but we'll cover something called fine-grained multi-threading. I'll give you the basic idea. It's always good to know the basic idea first. The idea is, if you know that some other thread has no register dependencies, and that's the definition of a thread, right? You execute some other thread. Basically, another way of putting it is, ensure that no instruction, no dependence, no 2 instructions are in the pipeline from the same thread at the same time. Right? So we have let's say we have a 5-stage pipeline: fetch, decode, execute, memory, write back. The problem happens because a data dependency may exist because you have 2 instructions from the same thread in different pipeline stages at the same time, right? But if you ensure that the pipeline stages are executing instructions from different threads, we have no problem, right? You have thread 0 here, thread 1's instruction here, thread 2's instruction here, thread 3's instruction here, thread 4's instruction here. While this thread 0's instruction is writing back, thread 1's instruction is accessing memory, thread 2's instruction is executing, thread 3's instruction is being decoded, and thread 4's instruction is being fetched. Now there are no dependencies between these instructions, which means that you're really doing something else in different stages that has nothing to do with what you're doing in the other stages. Yes?
You could still have a dependency on memory.
That's right, yeah. We're going to ignore that for now. We're not talking about memory dependencies. But you could even think that maybe you're not sharing memory at all, right, between these different threads. So this idea is called fine-grained multi-threading. And it has been employed in many processors, including today. And we'll get to that when we cover control flow handling. The key is ensuring that you don't have the 2 instructions from the same thread at the same time in the pipeline. So after this thread 0's instruction is retired or done, writes its result retard is another term for writing its result. Now you can fetch thread 0's instruction again, right? So this is, let's say this is cycle n. In cycle n plus 1, you can fetch the next instruction from thread 0, and the instructions move this way. Right? So you basically fetch from the same thread every 5th cycle. Right? Okay. We'll cover this in more detail. But it's a beautiful thing, right? You don't need to deal with any of the dependency handling. Of course, what if you have only one thread executing in the machine? Does this work? It doesn't, right? Actually, it works. Except you'll be fetching no ops. Basically, you still have you still fetch from different threads, except those different threads happen to be no ops, right? What you've done is essentially you're not utilizing your pipeline well if you do not have enough threads in the machine, if your machine is designed this way. So this is actually done in Sun Niagara, which we will briefly talk about. But it's a very old concept. Sun Niagara is a recent processor that did this. I guess Intel Larrabee doesn't exist anymore, right? Intel Larrabee actually has this fine-grained multi-threading design also. And we'll likely see a lot more designs with this because it does simplify a lot of things. Okay, actually all of these are in some way or form used in existing processors. Certainly pipeline processors, they use this. MIPS detects and eliminates the dependence at the software level, like initial MIPS. And we'll talk about that a little bit. Yes?
So when you do something like this, you're not actually finishing an instruction in that cycle.
So you're finishing one instructions from the same thread every 5 cycles. Right? You're still finishing one instruction every cycle, assuming you can keep the pipeline full, but they're from different threads. But from the same thread, you're finishing one instruction every 5 cycles. So if you have only a single thread in the system, then you're not utilizing your pipeline well. Okay. Okay. So let's delve into some of these in a little bit more detail, since you're going to implement some of these in your lab. But interlocking, I've given you the definition before. This is the detection of data dependence between instructions in a pipeline processor to guarantee control and correct execution. Who does this? The software can do it, as we've seen here. This is software-based interlocking. Or hardware can do it. And I don't have it here, but I'll show you how the hardware can do it. Let's look at the software form. Well, if the software does this, then hardware doesn't need to do any interlocking, right? And MIPS, initial philosophy of MIPS was, let's keep the hardware simple. Let's have a pipeline processor, and for the original implementations of MIPS, let's have a pipeline processor, but ensure that the software guarantees correct execution in the presence of dependencies. So original MIPS was designed to be that way. That's why it's called microprocessor without interlocking pipeline stages. Right? That's what the acronym means. But of course, over time, what people figured out was it was actually hard to do this. You need sophisticated compiler-based scheduling algorithms to do this. And in the presence of operations with variable latency, this is tough to do. So if what happens if your load sometimes takes 2 cycles, sometimes takes 100 cycles? Are you going to have 100 instructions to fill here? It turns out that's tough. Compiler is not always capable of finding independent instructions. So existing MIPS implementations, I guess there are some that still exist, right? MIPS is still around, yes. Most existing MIPS implementations use hardware-based interlocking. But you can imagine having software scheduling aid the performance, right? Because you may not be able to always eliminate these dependencies in hardware. Okay. So how do you detect dependencies in hardware? Let's take a look at that. There are 2 ways. One is scoreboarding. It's described here. Well, let's do this. The idea is simple again. You have the register file. You add a valid bit. Let me put this register file to the left. This is the one you... Now where we place the register file actually matters, because I'm going to use an example. So you have the register file. For each register in the register file, you have a single bit saying, is the register's value available? This is called a valid bit. And initially, everything is available. And remember where the register file actually sits. This is the fetch stage. This is the decode stage. This is the execute, memory, write back. When an instruction is decoded, what it does is it checks if all of its source and destination registers are valid. If they're all valid, it's good to go, right? It basically checks the 3 bits, or depending on how many sources and destinations it has. If they're all valid, then there's no need to stall. There's no dependence. Otherwise, it needs to stall. And an instruction that writes to the register file, here, when it's decoded, let's say you have an instruction that's writing to register 2, it resets the valid bit of register 2. And then it keeps executing. And once it writes back the register 2's value, at that point, it sets the bit back to valid. Make sense? So it's a very simple way of detecting dependencies. You have valid bits, and you just check the valid bits and update the valid bits at the right place. What is the advantage? Well, it's simple. 1 bit per register. What is the disadvantage? Any guesses? Well, now you need to stall for all types of dependencies, at least the way we designed this, right? I told you that an instruction decode stage checks if all of its source and destination register are valid. But we really want to stall for read after write dependencies, the true dependencies. But now we're stalling for write after write and write after read dependencies also. So what changes would you make to the scoreboard to enable not stalling on anti and output dependencies, or write after write, or write after read dependencies? Would this work, for example, if you just checked the source registers? So I'm going to eliminate one thing here. An instruction in decode stage checks if all its source registers are valid, not destination register. Would it work? Some of you say yes, some of you don't know. I would argue that it doesn't work, at least for all cases. Why? At least the way I described it, right? Let's say you have a multiply. I pick multiply that's writing to register 2. It sets the valid bit to 0. And the multiply goes on. And then, I don't know, you have a branch somehow. And then you have another add writing to register 2. Well, add can move, assuming that sources are valid. Add can move. Multiply already moved. Now you have this multiply writing to register 2 and add also writing to register 2. Right? Its sources are valid. That's why it can move. And we're not checking the destination register. R2 is 0. But we're not checking it. So this multiply writes to R2. And this branch goes on. And this multiply also writes to R2. And then let's say this add. And we don't care what it's reading and writing, but let's assume it's independent. At this point, this multiply writes to R2 and sets the valid bit to 1. And let's say the value is 5, right? And then this multiply is gone. Now you have this branch that's moved here, assuming it's correctly predicted and everything. You have the second multiply writing to R2. producing a different value, hopefully. And then you have this add that moved to this stage. And now let's say we got an add that reads from R2. Well, it's valid, right? So it gets the value 5, which is the wrong value, because it should get the value that's going to be produced by this multiply, right? So the simple scoreboard design as I described doesn't work. So how do you make it work? So this is clear, right? So you need to somehow ensure that this multiplies result is communicated to this adds result. We still want to keep the scoreboard, but we want to get rid of this condition where an instruction, the decode stage, doesn't wait for its destination register to become valid. If its source registers are invalid, then it should wait. Any guesses? How would you modify this design simply to fix this problem? Oh yeah. Who wants to go? You can arbitrate.
Have two different scoreboards for read and write.
Have two different scoreboards. I had to think about that for read and write. Would that work? If the two instructions would still be writing to the same scoreboard, right? Yes, let's see if we can improve upon the solution.
Have a counter that counts up to like as many stages you have after the reading.
Okay.
Register file, and when it goes back to 0, like never write back, it will decrease it by 1. When it goes
Okay.
back to 0.
I see. I think I understand what you're saying. Basically, instead of having a valid bit, have a valid counter that counts how many producers of the same register are in the pipeline. And when that counter is 0, then you know that all of the producers have written their values. Now the instruction that's reading the register is safe to go. That should work. Does that make sense? Basically, instead of having a valid bit, have a counter. When an instruction writing to that register is being decoded, increment the counter. In this case, when the first multiply is decoded, this counter will become, well, I guess you need to reverse it. Now it's not, it's kind of like the invalid counter or write counter, right? How many instructions are writing? Let's get rid of the valid bits and call it the write counter. Initially, everything is 0. And if the source registers have write counter 0, meaning no writers in the pipeline, the instruction here can move. When that multiply is being decoded, it'll become 1. When the next multiply is decoded, this will become 2. Now there are 2 instructions that are writing to that register. When the first multiply writes back its result, it decrements the counter to 1. After that point, this add comes in, checks if R2 is actually valid. Well, it's not valid because there's someone that's still waiting to write. So this add stalls. And when the next multiply, the second multiply, writes back its result, this becomes 0. Now this add can go. Right. Yes?
So this is like a semaphore for writing first.
Exactly. Yes. This is exactly like a semaphore. A semaphore is nothing. It's fundamentally data dependence handling. You're right. A semaphore also controls the data dependencies at a higher level of abstraction. So you can apply all of these concepts to any kind of data dependence handling, including multi-threading. Make sense? Now there are other ways of doing this actually. What you can do is you can, all right, I'll not discuss this, but you can, one other way of doing this is you could tag, instead of having this write counter, you could have a tag associated with each register that stores the ID. Let's say you have a unique ID for each instruction that stores the ID of the instruction that's writing to the register. Does that make sense? So you basically when an instruction comes in, you tag the instruction. Instruction 0, 1, 2, 3, 4, dot, 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 dynamically. And when instruction that is being decoded is writing to a register, it writes its tag here. In this case, let's say multiplies tag sequence number. So a tag could be a sequence number. Tag of an instruction. Could be also the sequence number of the instruction. And when an instruction that's being decoded is writing to a register, it sets the tag of this destination register to be its sequence number. Let's say that initial multiplies sequence number was 10. It sets it to 10. And then that multiply goes on. The next multiply comes in. It sets its sequence number to, it sets the sequence number of R2 to 12. Because remember, there was a branch in between. So now, this is the tag of the register. And there's also a, okay, this is a tag of the register that's going to be written. When this first multiply is in the write back stage, what it does is it sends its tag to the register file. And the register file you compare. Remember, the tag of the first multiply was 10. Does this 10 match 12? Well, it doesn't, right? Which means that this multiply is not going to write to the register file. Make sense? And of course, you may need something else like a valid bit. Actually, let's do that. You also have a valid bit that's set to 0 when an instruction that's writing to that register is decoded. Because these two tags do not match, this valid bit still stays 0. And now we fetch this add R2. Add R2 checks if this valid bit is 0. Well, it's 0. Then add R2 cannot go. Now the next multiply is writing back. When that writes back, its tag is now 12. Right? The logic here checks if the tag matches the destination, the tag of the register. It does. When it's writing to R2, you also have the register ID. If it matches, now you write the value into the register file, 5, and set the valid bit to 1. Which means that now the correct value of the register is produced. Now this add that's here waiting for R2 can go, right? Because its valid bit, the valid bit of R2 is 1. Make sense? So what we've done right now is added a tag to ensure that the correct writer writes to the destination register, right? You can think of this as the last writer tag. This is the instruction, identifier of the instruction that's going to write to this register the last in the pipeline, semantically. This is important because we'll see how this is useful in out-of-order execution. This is what enables out-of-order execution. What will happen, now I'm looking forward a little bit, is now what we've really done here is we've said R2 is going to be produced by instruction 12, right? We've kind of renamed R2. And you'll see this when we cover out-of-order execution. This is called register renaming. Remember, we have few registers because we don't have enough names. Now we're really renaming R2 to this tag. R2 is going to be produced by this instruction with this number. Now imagine what you can do with this tag is if an instruction is actually dependent on R2, you can say, oh, this is actually not dependent on R2, but this is actually dependent on the instruction with number 12. Now you can take this instruction out of the pipeline and put it somewhere and wait for the instruction that's producing 12, the tag 12. That's the idea in register renaming. Register 2 is renamed to tag 12. And the instruction that's waiting for register 2 at that point can be moved out of the pipeline, and it could wait for the instruction that's producing tag 12. Okay, that's about it for now for out-of-order execution. This will enable out-of-order execution when we get to it. Okay, but this is one way of actually handling the dependencies. You have a scoreboard, and with a scoreboard you can actually eliminate. You don't need to stall on anti and output dependencies, the false dependencies. Make sense? Okay. So what other ways do we have for handling dependencies? Well, you can actually have a combinational dependence check logic also. Basically, the idea here is not to have a central scoreboard here, but you have a special logic that checks if any instruction later stage is supposed to write to any source register of the instruction that's being decoded. So you could think of a combinational logic that takes in all of the destination registers here, destination register of the instruction the EX stage, destination register of the instruction in the MEM stage, destination register of the instruction in the write back stage. You have those IDs. And compares each of these separately to each of the source registers that is trying to be sourced here by the instruction that's being decoded. So that's another combinational dependency check logic now. Make sense? Of course, you need to be careful, right? And we will get to that. What if the instruction here is not writing to a register? What if the instruction here is not sourcing the register? So you need to check if the instruction is actually writing to the register, because you will still have a register ID here, even if the instruction is a branch, right? Because you're communicating those values from the instruction register. Some fields in the instruction register give you the destination register ID. But the instruction itself may not be writing to the register. So you also have, is the instruction writing to a register file? Is it a write? Is it a write here for the memory stage? And is it a write here to the write back stage? And you also check is the instruction sourcing a register, let's say register 1, and is this instruction sourcing or register source 1, register source 2. So you need to check those things to make sure you can detect the dependence. Okay, we'll get to that. We'll get to a design, and you will actually design this logic for your lab. So advantage, no need to stall an anti and output dependencies in this case, right? Is that correct? It is true, because you're actually checking sources and destinations only. Well, you still need to ensure that the values are communicated correctly. So you still need something like this. Disadvantage is logic is now more complex than a scoreboard, right? With a scoreboard, you have just one bit. Here, you have the combinational check logic. Make sense? Okay. And I'd like you to imagine again, this actually becomes more complex as you make the pipeline deeper, right? Think about it. If you have 30 more stages down here, which is what Pentium 4 had or Prescott had, do you do that from every stage? Well, that becomes a huge logic, right? Because you may have 30 different instructions writing to a register. And do you compare all of those register IDs to the source register IDs here? Expensive. That's why a scoreboard is a little bit more beautiful. But it's a trade-off. We will need something like this for data forwarding. Yes?
You could do the same thing using tags and scoreboard. Because the tag pretty much identifies which is the last instruction that goes. So for example, if you have, say, 4-stage pipeline, their tags could be a mod 4 number. And then the difference between the tag and your own tag is actually how many instructions forward is the instruction that should be generating your result. So you can directly just max into like the forwarding unit. I want this instructions of data.
That's right. I like your thinking, and that's you could do similar things with the tags. You're right. For forwarding. Okay. I guess once you detect the dependence in hardware, what do you do afterwards? Basically, one observation is that dependence between two instructions is detected before the communicated data value becomes available, right? The data is not available, but you know the dependence. So one option is you can stall the dependent instruction right away, right? But that's not the optimal solution. You can actually stall dependent instruction only when necessary. Only when necessary means you can move the instruction as long as you know that the value that's going to be produced by the instruction, producer instruction, can be correctly communicated to the dependent instruction. Right? You don't need to stall it when you detect the dependence. You can move it as long as you communicate the value correctly. The key is really communicating the value correctly. And this will lead us to data forwarding and bypassing. Well, I guess you could have other options here, but I'll let you imagine that. So I'll give you one possible option, which we will talk about later on. For some dependencies, what you can do is once you detect the dependence, you can say, oh, I'm switching to another thread. Right? Instead of doing it every cycle, switching to another thread, you could say, if you have hardware support for this, of course, you would like to switch quickly. When you detect the dependence, you say, let's bring in another thread, because this thread cannot move. Okay? And that's another idea in multi-threading. This is also coarser-grained multi-threading in hardware. And this is usually done with dependencies that go to memory. So if you have a load instruction that misses in the cache, that's going to take 100 cycles. And if you fetch a dependent instruction, what you can do is bring in another thread instead of keeping executing on the same thread. And this is actually employed in many processors also to tolerate the latency of long latency loads. Okay, so I'm giving you a lot of ideas here. But let's take a look at this in a little bit more detail now. Or do you guys want to have a break for 5 minutes? Who wants a break? Okay, let's have a break for 5 the and then we'll continue. Basic idea. The fundamental problem is a consumer, I'll call it a consumer, a dependent instruction is a consumer, right? Has to wait in the decode stage until the producer instruction writes its value into the register file, right? And our goal is we do not want to stall the pipeline unnecessarily. And the observation is that the data value that's needed by the consumer instruction can be supplied to supplied directly from a later stage in the pipeline, right? Supplied directly from the producer, instead of waiting for the producer to write to the register file. And the idea is simple. Once you make this observation, basically you add additional dependence check logic and data forwarding paths to supply the producer's value to the consumer right after the value is available. So instead of having producer and consumer communicate only through the register file, let's say you have an add instruction that executes. You don't wait until the add instruction writes the register value to the register file, but you forward the value such that the add's result can be used right away. Similarly, a load instruction that accesses data from memory, you don't wait until it writes its data all the way back to the register file, but a dependent instruction can now get the data from the memory here and execute it with that data. That's the idea. The benefit, basically, now the consumer can move in the pipeline until the point the value can be supplied. You have less stalling in the pipeline. And we will see, actually, you will implement in your lab how to do this. Now we'll go a little bit more deep. And I'll go faster because I've given you all of the fundamental concepts, I think. We'll go into implementation soon. But before we do that, there's a special case of data dependence, which is control dependence, right? And as we've discussed last time, this is a special case of data dependence because its data depends on the instruction pointer, program counter. So, but it's special because it affects something. You've got to resolve this data dependence very, very quickly. Otherwise, you don't know what to fetch, right? what should be the fetch PC in the next cycle here? It should be the address of the next instruction, right? Next dynamic instruction. And all instructions are control dependent on the previous ones because every instruction modifies the program counter, right? Now, if the instruction is not changing the program counter to something other than the next instruction's program counter, this is trivial. That's the beauty of the von Neumann model, right? You always go to the next program counter, unless you have a control flow instruction. So if the fetch instruction is a non-control flow instruction, next fetch PC is the address of the next sequential instruction. It's trivial to determine unless you have a variable length instruction, right? Now we have a variable length instruction. You have to decode the instruction to figure out the next PC. So you may have a bubble in the pipeline when you're fetching if you have a variable length ISA. Okay, I'll let you think about that. This is where things get complicated with variable length ISA. But if the instruction that is fetched is a control flow instruction, then there is even a bigger problem. Now we don't know what is the next fetch PC, right? If it's a branch. Because you don't know if the branch will be taken or not taken. Second, you don't know what the target address of the branch is. Well, you don't even know if that instruction is a branch, right? You're fetching the instruction. You haven't even fetched the instruction yet. Yet in the same cycle, you need to determine what you should fetch in the next cycle. This is a branch. You don't know if it's a branch. If you do not do something about it at that point in time, this branch will move here. You will figure out that it's a branch here, but you have no idea what this is here, right? So you really need to determine whether this instruction is a branch in the same cycle that you're fetching it. So the problem is more difficult than it looks, right? You don't even know that instruction is a branch. You don't even know that it's going to change the control flow. And we'll look at how to ameliorate this problem in the next lecture in detail. But let's look at the data dependence handling in more detail. I think I have a lot of slides, and I'll go through them relatively quickly. This is your implementation. This is, remember, the data dependence types. We have 5 fundamental ways of handling these data dependence types. And the issue is, if you follow the flow dependencies, these lead to conflicts in the 5-stage pipeline, right? So let's assume that you have this add that's writing to register A, and all of the following adds reading from register A. Well, you've got to wait until this add writes to register A, which means that you really have this conflict. If you do not handle this somehow, that's why this is called a hazard, right? I don't like the word hazard, but if you don't handle the dependence correctly, you'll have a hazard. You'll get the wrong result. That's the idea here. So you can actually use this result only after this point, I believe, because this add, well, you don't want to use this result because these adds also need to get the right value. Okay, so let's analyze these data dependencies a little bit. This is the control logic that you're going to build at some point. If we have the instructions here, different types of instructions, and different stages in the pipeline here, we know what instructions need to read the register file. I guess all types except for the jump instruction, which is based on the program counter, need to read the register file. And we know what instructions need to write into the register file in the write back stage. So for a given pipeline, when is there a potential conflict between 2 data dependent instructions? You can figure this out by looking at the instruction type and by looking at the distance between the instructions also. And that's what you're going to do. So a little bit more theoretically, basically, when can you move the pipeline? When is it safe to move the pipeline? When is it safe to move an instruction in the pipeline? Let's say this is the read after write dependence. This is the register write stage, and this is the register read stage. And we can call it stage X and stage Y. And this is the instruction I and instruction J. Instruction I is writing to a register, producing a register. Instruction J is consuming. Now, it's safe to move instruction J in the pipeline if the distance between the instructions is greater than the distance between when the value is written and the value is read. Make sense? Whereas if the distance between the instructions is less than the distance between the register write and register read stages, then you cannot move the instruction. And this is actually, you can think of this from a compiler point of view, right? Compiler needs to guarantee this when it's scheduling instructions if you don't have hardware-based interlocking. So these theoretical analyses are useful in the compiler community also when you design a compiler. Essentially, that's what the compiler does. The compiler determines the distance in terms of the stages between the register write and register read stage. And it tries to move the instructions that are dependent such that their distances in the instruction stream is greater than the distance between the register write and register read stages. Make sense? And the hardware is doing the same thing when you're doing the hardware-based interlocking. Okay, if you look at, in a pipeline, write after read dependence, you can do the same analysis, basically. Let's look at the write after write dependence. In a pipeline as we designed, if you look at these things, the distance between instruction I and j has to be greater than or equal to 1, right? But the distance between register write stage and register write stage, that's where the dependency exists, is 0. So it's always safe to keep moving the instruction that writes to the register, assuming you design the right hardware, of course. Okay. So basically, instructions IA and IB have a read after write dependence if instruction B reads a register written by instruction A. And the distance between those instructions is less than the distance between the instruction decode and write back stages. And I'll let you think about these other dependencies. We'll talk about memory later on. We're going to ignore memory for now. But memory also leads to data dependencies, right? The difference is you do not know the memory address until you execute the instruction. Whereas with register dependencies, you know the register address. So register dependencies are easier to handle. Memory dependencies are a little bit harder to handle, but we will see that. Okay. So basically, how do you resolve this data dependence? If you look at this, let's say instruction I and j, I is consuming a value that's being read by j. Their distance is 1, which means that, but really their distance should be 3, I think. Which means that you need to insert bubbles such that their distance becomes 3, right? Well, I guess in this case it's 4, becomes greater than 3. Make sense? So that's what a bubble is, essentially. You're basically increasing the distance between the instructions. And you could view this as done by the hardware, which is what this is, and done by the compiler. The compiler needs to fill the bubbles with something useful, or if nothing useful, no ops. Okay. So a stall, what is a stall? You make the dependent instruction wait until its source data value is available. You stop all upstream stages and drain all downstream stages. So you stop upstream stages are stages to the left, downstream stages are stages to the right. Okay. So how do you actually implement stalling? Well, it's simple, right? You basically ensure that the program counter doesn't change because you're stalling the upstream part of the pipeline. And you also ensure that the pipeline registers, so let's say you're stalling here. This is where you detect the dependencies. You need to ensure that the program counter doesn't change, and you need to ensure that this register doesn't get written, right? And you ensure that stalled instruction stays in its stage. And what also you need to ensure is you need to insert invalid instruction into the stage following the stalled one, right? So for example, you detect the dependence of an instruction here. In the next cycle, this instruction should not move to the next stage. Instead, an instruction that's invalid should move to the next stage. Well, how do you do that? Now each pipeline register has a valid bit associated with it. Each pipeline register can be valid, can be carrying an instruction that's valid or invalid. I guess I don't know, I don't have it in that picture, but. So a visual way of thinking about it is, at least I like thinking about it this way. You basically have a valid bit associated with each pipeline register. And stalling a pipeline stage basically means that, let's assume that these are valid. Let's say we're stalling the instruction that's here. Well, this is the decode stage. You have a valid instruction here that you're decoding. You checked and figured out that the instructions downstream are producing the value. This is dependent on something else. What you need to do is you keep the instruction waiting here, and the next instruction moves to the next stage, and the next instruction moves to the next stage, and the instruction that you insert here is basically a bubble. It has a valid bit of 0. And you don't need to change anything here, right? As long as this valid bit is 0. Hopefully, you'll gate everything you do in terms of writing and reading to the architectural structures with this valid bit. Make sense? So that's how you can insert a bubble. This is one way. Another way to insert a bubble is to set the control signals such that those control signals indicate a no-op, right? That way you don't need these valid bits. That's another implementation, right? And I'll let you think about the trade-offs between the different implementations. They all achieve the same thing architecturally. Okay. Let's see. Basically, how do you implement the stalling? You must stall when instruction B is in the ID stage and wants to read a register that's to be written by instruction A in the execute memory or write back stages, and this is basically the logic. This is the logic that I kind of sketched here. Well, I guess it's escaped us now. Somewhere over there. Wow. Yeah. Okay. I'll get it back. Yeah, this is this logic basically. If an instruction is using the value produced by any of the instructions over here, and those instructions are actually writing to that register, then you stall. So you basically have this combinational logic that implements stalling. Does that make sense? I'll go through this relatively quickly. But this is essentially what you are going to implement in your lab. I guess I'm giving you too many hints, right? Yes? Some of you say yes. Okay. So what is the impact of stall on performance? Let's do some performance analysis also. Each stall cycle actually corresponds to one lost ALU cycle, right? And for a program with n instructions and s stall cycles, average cycles per instruction now becomes n plus s divided by n. And now your s, the stall cycles, really depends on how often you see these dependencies, read after write dependencies, the exact distance between the dependent instructions, and also distance between the dependencies. So basically how much you stall in each cycle. So let's take a look at one example, sample assembly program. This is from your book, actually. But this is a string of instructions that have lots of dependencies. And this implements, believe it or not, this for loop. And ... is here. So if you look at this, you have a lot of dependencies, right? This SLTI instruction needs the value produced by this add instruction. And that's not produced until after 3 cycles in the 5-stage pipeline that we've looked at. Similarly, this branch needs the value produced by this SLTI instruction. Again, 3 cycles. So if you look at this, you get a lot of stalls. And we're going to fix that problem with data forwarding soon. So I've given you the idea of data forwarding. You can study these slides also. But basically, the key observation is that register file just keeps state. Whereas what you really want to do is communicate values between producers and consumers. So how do we ensure that the value is communicated? I'll let you read those slides. So what really matters is the maintenance of the correct data flow between the operations. Right? So you don't really need to wait until data is written to memory. As long as you maintain the correct data flow. Remember data flow architectures? Now we're moving to that a little bit. We're trying to communicate the data correctly between different operations, between producer and the consumer. And we're going to do that even more when we get to out-of-order execution. So that's what data forwarding is. When the value is available, forward it quickly. Don't wait until it's written to the register file. Because register file is visible to the programmer, right? You want to write to the register file in program order, because we still have the von Neumann model. And the instruction needs to go to the write back stage to write to the register file. But the value is actually produced much earlier. This add instruction already produced its value after the execute stage. There's no point in waiting to execute the dependent instruction until this add instruction writes its value into the register file. It can bypass the value to a later instruction. Let's take a look at how we do that. Basically, instead of doing this next add waits until this instruction writes its value to the register file. When this first add produces its value, which is here after execute, the next add can execute right away, captures its value. Okay? So how do you do that? Well, you can read this again. This is going to help you with your implementation in the lab. That's why I'm going this relatively fast, because I've given you the concepts already. But basically, you would like to retrieve the operand from the data path instead of the register file. That's the key idea. And moreover, you would like to retrieve the operand from the youngest definition if multiple definitions of the register is outstanding. Right? Again, it's about the value. It's not about the register ID. If there are multiple instructions that are writing to register 2, as I showed you earlier, and there's one instruction reading from register 2, this should get the latest value written into the register 2, because that's the real producer. Right? Okay? So you need to ensure that this happens if you would like to implement data forwarding. So how do you implement data forwarding in the pipeline that we've shown? This is the pipeline before, and we're going to add some muxes, basically. Now the values can come from the register file, but not only that, the values can come from the output of the ALU, or the value can come from the output of the memory. Let's take a look at this mux. The value can come from the register file. The value can come from the output of the ALU here, if I can follow these paths. The value can come from the output of the memory. And the value can come from the write back stage. Right? So there are 4 different places where an instruction can capture its value, because there are 3 stages later on and the register file. Right? So if you'd like to forward the data produced by any instruction that's later, you would like to be able to figure out where this instruction needs its value from. So how do you do that? In this case, basically the distance between the instructions is 1. If the producer is an ALU instruction and the consumer has a distance 1, these can execute back to back. There's no need to stall, because you have this forwarding path, right? This add operation produces its result. This multiply operation that's dependent on it captures that result and executes in the next cycle, because we've provided this additional path. It's beautiful, right? And if the instructions have a distance of 2, let's say this is the load instruction. It could be the add instruction also, actually. For example, if you have an add instruction here and another add instruction that's dependent on it with a distance 2, you can still forward that value here, right? Basically, you can forward the value of the producer from any stage back to this stage. If you have a load instruction and a dependent add instruction, now that add instruction can get that value only here. You need to insert 1 stall cycle, right? Because if you let the add instruction move, it would have executed with a stale value or incorrect value. But the load instruction's value, the produced value, which is the source of the add instruction, is available after the add is executed. So you still need to insert a bubble when an add instruction is dependent on the load, just because the pipeline is laid out this way. Right? Make sense? So, and this is the forwarding path for instructions that have a distance of 3. And you can imagine all kinds of dependencies can be this way. Well, actually, you don't necessarily need this forwarding path if you have this forwarding internally in the register file, right? Remember what we've assumed? A register is written in the first half of the clock cycle, and that value can be read in the second half. That's kind of like an internal forwarding, right? Except you don't need to check whether you need to forward or not. If you can do that, then you can eliminate this forwarding path. Okay? Because you can concurrently write to a register and read from it in the same cycle. Okay, another way of looking at this is, so here, look at where we place the muxes. The muxes are right after the register file, right? Well, you could have them before the ALU also, right? Instead of placing them right after the register file, you could place them right before the ALU. And this now is a design decision that you need to make depending on where the critical path is, right? And the forwarding paths are very similar here. Basically, an ALU operation forwards its result after it latches its result. And the next operation can capture that result right before it starts executing in the ALU. Right? This will not be a forwarding path, right? If you do this, that will be a loop, and that will be incorrect. So be careful when you design your machine. Don't have a loop from the output of the ALU to the input mux of the same ALU. That could be a mistake, actually, in the design, yes.
Do they ever, like you can time it, though. Like, you can have an asynchronous circuit.
That's right, yes.
Do they ever do that?
That's very tough to design. There are designs that can use asynchronous logic, but that's very tough to design. Especially loops are very, very hard. It's very prone to bugs. Okay, and this is the other path for instructions that have a distance of 2. Again, muxes are here. And, well, here we assume this internal forwarding in the register file. So what is the data forwarding logic for this version 2? Basically, it's this. If the register source in the execute stage here, it needs a register. If the instruction in the execute stage needs a register, and the instruction in the memory stage is writing a register, and the register IDs of the instruction in the execute stage and the memory stage match for the destination in the memory stage and for the source in the execute stage, then you make sure the mux gets the data from the memory stage. Then you enable the mux to get the data from this stage, basically. Similarly, you do the same thing for the write back stage, right? And otherwise, you get the operand from the register file. So it's a relatively simple forwarding path. Of course, you need to somehow determine these signals, right? Ordering matters. You must check the youngest match first. So you must check memory stage. Is the memory stage producing a result for the execute stage before you check the write back stage? If you do the ordering right, then you'll get the wrong answer again. And I guess why doesn't use RS appear in the forwarding logic? Any guesses? Use RS, I didn't define it quickly, but basically use RS means, are you actually using the register here? Basically, the forwarding logic sets up these muxes, right? Use RS means you need to check somehow whether the instruction in the execute stage is actually using a register, right? Why don't we check that? Well, because something else, we just set up the muxes with the forwarding logic here. We still forward the data, but if the instruction is not going to use the data, we're not going to care about it anyway, right? So this is just setting up the muxes. Okay. I guess what does the above not take into account? I guess it depends on how you design the pipeline, actually. But if you actually have a design with valid bits like this, you'd better check if the instruction is valid, right? Although you could argue that that reg write is gated with the valid bit. Right? Okay? So when you're designing your pipeline, you've got to be careful and ensure that invalid pipeline stages with invalid operations, do not forward the wrong data. Okay? Because that could affect the correctness of this. Okay. And I think I've already given you, basically, you can think about it. Now we've moved from writing from the register file, where it's reading from the register file. But now we're thinking about when does an instruction produce its value, and when does an instruction consume its values. If you think of it that way, now you can forward the data between any stages. For example, an R-type or I-type instruction produces the value in the execute stage and uses the value in the execute stage. So you can forward in one cycle. But even with data forwarding, we've seen that a dependence on a load instruction requires a stall, because you need that value to execute in the ALU. Okay, so if you revisit the assembly with lots of stalls, and if you do data forwarding in this assembly, as we've described, you only need a no-op after the load. The only data dependency you cannot eliminate without this forwarding is this load to SLT dependency. Okay? And you can look at that. Okay. So I think I'll leave this as an exercise to you, but pipelining the LC3B, that handout describes how you can move from a design like this, the single bus data path, to a pipeline data path. Basically, that handout divides it into 5 stages: fetch, decode, address generation, memory, store result. It's a conservative pipeline design. Basically, it stalls on a branch, and we will see why this is so bad in the next lecture in detail. And it stalls on flow dependence, and you've seen why this is so bad in this lecture, right? And the design looks like this, basically. It's a design that has valid bits. It has a control store ROM, and these are the control signals. And I'll let you read the handout. How many of you have read the handout, by the way? Is it interesting? Would you like to implement it? No, you're going to implement the MIPS design, but this is just to show you another design. And these are the control signals. So I think I'll leave you here, and we'll meet Friday to discuss control dependence handling. No questions? Okay.